let's turn to page 4. I know we got started with this 4.01 practice. And I would like to continue to work on this. I expanded this page out just so I can show more work as I go through with you. But this is page 4. If you feel like you need some additional space, you can use additional sheet, but I just want to be able to go through most of these problems with you, so that we'll try to do some of the practice on page 4, and then we can move into the new section for today. But it's really important that we get comfortable with these properties. Okay. So I'm going to start from the beginning again. Start with number 1. Again, what we're trying to do is to simplify the following expressions and match them with their solution. Connect the number of the questions with the letter of the solution to create a picture on the next page. Okay, so anytime we see an exponent of 2, we're always going to be looking for opportunities to potentially involve some sort of a work. It could be applying a reciprocal or Pythagorean identity. It could be factoring. It could also be something that we're going to see with something involving difference of squares. So for number 1, we know that secant squared x minus 1, there is a Pythagorean identity that looks like it. So we're trying to find one that is equivalent to secant squared x minus 1. If I just subtract 1 from both sides, I can get secant squared x minus 1 to be equal to tangent squared x. Right? And that was key, right? Some of these are pretty straightforward. We can rely on reciprocal identities to get there. So 1 over sine x is just going to be cosecant x. Okay, number 3, sine x cotangent x. We know that we can't do much with sine, but we can do something with cotangent. Cotangent, if I can get it in terms of sine and cosine. And we see that cleanly comes out to be just cosine. Okay, number 4, sine squared over 1 plus cosine x. I'm not going to do anything with the denominator, but the exponent is what's going to draw me to want to do something with it. Okay, so sine squared, I see I have an identity for sine squared. I'm going to see if I can rearrange to find an equivalent for sine squared and subtract cosine squared from both sides. So I know that sine squared is equal to 1 minus cosine squared x. Okay, we make that substitution. Okay, we talked about how this is really a difference of perfect squares. Right? We know that there's a rule that says a squared minus b squared can be broken down into a minus b times a plus b. In the same sense, we can break 1 minus cosine squared x down into perfect squares, or down from perfect squares. So we know that 1 minus cosine squared x can be written as 1 minus cosine x times 1 plus cosine x. Okay, is everybody okay with that? All right, so we use identity to get it in terms of cosine, but we can't just cancel out, right? We're breaking rules if we do, but we do have something that we can do with difference of squares. Okay, we get the numerator. Get the parentheses to cancel out. for 3 is Q. Okay, number 5, 1 plus tangent squared x. I see an exponent. I'm looking for something that I can replace. 1 plus tangent squared x. Okay, just secant squared x, right? Okay, next up, cosecant squared minus cotangent squared x. I see exponents. I'm looking for a trig identity, a Pythagorean identity that I can use. If I subtract cotangent squared from both sides, I can get this to be cosecant squared minus cotangent squared. And that's just equal to 1, right? Okay, are we okay so far? Okay, next up, cosine squared over 1 plus sine x. I see an exponent involving cosine squared, so maybe I can use this identity here to get this in terms of sine. This is going to be similar to what we did with number 4. So that cosine squared can be rewritten as 1 minus sine squared. Okay. We can work with that 1 minus sine squared. We can't cancel out yet, but we know we can do something with it. Not much we can do with 1 plus sine x, but we have perfect squares here. So we can break them down into perfect squares. Much like how we did here with 1 minus cosine squared x. I can do the same thing here. 1 minus sine squared x can be broken down into 1 minus sine x and 1 plus sine x. Good so far? Okay, cancel out. So number 7 is going to be t. All right, number 8. Okay, number 8 is a little messier here. We got sine x plus cosine x over sine x cosine x. Notice that there's no exponent. So we know it's not going to match with any of these Pythagorean identities. But maybe we can split this into individual fractions. We can kind of separate them into smaller parts and then work on them individually. So that's what we can always do that if there's only one term in the denominator. So I'm going to split this up into 2 fractions here. Okay, is everybody good from this step to this step? All right, we're just splitting into individual fractions. And now within each fraction, there's some cleanup that we can do, right? What can we do with the first fraction? Take out the signs. And the second fraction, cosine. Now, looks like there's nothing remaining in the numerator, but there's still a what remaining? There's still a 1, right? We don't want to just lose that 1 or think that the denominator just comes up without any adjustments. So we're left with 1 over cosine x plus 1 over sine x. Okay. Is there a cleaner way to represent 1 over cosine plus 1 over sine? Yeah, secant and cosecant, right? We have reciprocals using our reciprocal identities. Number 9, cotangent squared x over cosecant x minus 1. I'm instantly drawn towards that exponent. That exponent is kind of helping me to identify, okay, maybe there's an identity that I can use here. And I know there's one for cotangent squared x, right? If I want to find a replacement for cotangent squared x, I can say cotangent squared x is equal to cosecant squared x minus 1, right? If I subtract 1 over, I can have a clean substitution for cotangent squared x. Again, we can't cancel across addition or subtraction, but hopefully you've seen this enough where what can we do with this cosecant squared x minus 1? Yeah, difference of squares, right? Difference of squares. So reduce, cosecant of x plus 1. Okay, number 10, 1 over tangent x. What can we do with 1 over tangent x? Make it cotangent. One over cotangent x. Reciprocal here, tangent. Okay, number 12, cosine over cotangent of x. Typically, if I see something that, if I'm trying to figure out how to reduce between trig functions, I'm thinking, how can I get everything in terms of sine and cosine? I know that everything that is not sine and cosine can be converted. So the cosine is already simplified in terms of our trig function. It's the cotangent that we can get to a different form. How can we represent cotangent? Yeah. So we know that dividing by a fraction is the same thing as multiplying by the reciprocal. So I can say cosine of x times the reciprocal. Right. We flip that denominator up as the reciprocal. And now, what can we do here? Yeah, cosine goes away. Following along with me? Okay, number 13. Cotangent squared x plus 1. Yeah. So cotangent squared x plus 1. Same thing as cosecant squared. Okay, number 14, 1 over cosine. Secant. Okay, any questions so far? Okay, 15. Cotangent squared x over cosecant x plus 1. Again, I'm always drawn to the exponent of 2 because I know there's something that I can do to get that in a different form. So I spot cotangent squared x. I want to find a replacement for it. If I subtract 1 from both sides, I get that cotangent squared x to be equivalent to cosecant squared x minus 1. Now that I have cosecant squared x minus 1, careful, we can't cancel out. But these are both perfect squares. We can break them down into a difference of squares. Basically, it's applying a squared minus b squared. All right, can be broken down into a minus b times a plus b. We get the like terms to reduce, and we're left with cosecant of x minus 1. All right, number 16, sine squared plus cosine squared x plus 1. Do you see maybe a substitution that we can make with number 16? Well, there's no equal sign here, so we don't want to just create an equal sign. Place. Yeah, we know that we know what sine squared plus cosine squared is equal to, right? So I can take that out and replace it with what? 1, yeah, and then 1 plus 1. Okay. Is everybody okay with that substitution? All right, we see sine squared plus cosine squared. I know that ultimately that's equal to 1. I can pull that out, replace 1 into it, get that to be cleaned up. Okay, number 17. 1 minus parentheses secant squared x minus tangent squared x. Maybe there's something that I can do to replace that. I do have a trig identity involving tangent and secant. So I can rearrange this, right? Say that 1 is equal to secant squared minus tangent squared. We have a clean substitution for this piece. Replace that parentheses with 1 because we see that's equal to 1. And then 1 minus 1 is 0. (18) Cosecant squared x minus 1. Okay, rearrange this, right? Subtract 1 from both sides. Cosecant squared x minus 1 is just equal to cotangent squared x. Yeah. Okay. 1 minus sine squared. There's an identity there as well. 1 minus sine squared equal to just cosine squared. Number 20 and 21, they're both kind of similar. I'm drawn to that x, the numerator. I know I can play with that numerator to get it to be a different form. I know tangent squared is equal to secant squared x minus 1. Perfect squares in the numerator. Continue breaking that down. $21 is virtually the same problem. We're just canceling out a different parentheses. Okay, 22. Negative parentheses sine squared plus cosine squared. Yeah, negative 1. I can replace the parentheses with 1. There's a negative hanging out, so it's just negative 1. $23. It's one messy fraction. There's no exponents involved here, but we can maybe separate into individual fractions and then break it down from there. Reduce, reduce, and simplify. We got 1 over cosine x minus 1 over sine x. Reciprocal identities. Okay, careful with these here. 1 minus secant squared x. What do you think 1 minus secant squared x is going to be equal to? Yeah. Careful with the rearranging here, right? If I want to subtract secant squared, I got to move that tangent squared over as well. This is the original identity. But if I want to get 1 minus secant squared x, I'm going to subtract the secant squared, but I have to move the tangent squared over as well. You got to be careful with this one as well. 1 minus cosecant squared x equals right, subtract cosecant squared over, but then we also need to move that cotangent squared over as well. Okay, how about 26? What can we do with this?
Substitute for 1.
Yeah, substitute in for 1, substitute 1 in for the expression. 3 times 1 is 3. Yes, question?
We have to memorize these identities?
The identities will be given to you on the quiz or test. Yes?
I'm still confused on 24, how you got negative.
Right. Okay, so are you good with tangent squared plus 1 equals secant squared?
Yes.
So I'm going to move things around. I'm going to subtract secant squared to the left side, but I'm also going to subtract tangent squared to the other side. So are you good from here to here?
Oh, okay, yes.
Good, yeah. So now that I made that arrangement so that I can see I have a perfect substitution, and that's the negative tangent squared. Okay, questions? Okay, let's go to the next section here, 4.02. At the end of class, I want to come around and just check that you guys have these problems finished, so I can give you class credit 1 through 26. Okay, let's go to page 6. Okay, we have these cofunction identities. Do you remember when we were graphing sine and cosine? We were able to do shifts of graphs between sine and cosine, and we saw that sine and cosine were just basically the same versions. They're just staggered versions of each other, right? So that's what these properties our identities are showing us, is that if I shift sine over involving pi over 2, I can get cosine of x to show up. So we know that sine and cosine has that shifted relationship with each other. And the same with tangent and cotangent, and also same between cosecant and secant. So these identities allows us to convert one function to the other if it's following these identities here. Okay. So you guys remember on the partner quiz where you guys had to create a sine version of a cosine function or cosine version of a sine function, and you had to just kind of shift the graph a bit. That's what that's demonstrated with these identities here. Okay, so cofunctions are translations or shifted versions of the same graph shape. Okay. Let's talk about even and odd functions. So have you guys copy this down here? So first step, first thing is even functions. So even function are functions that have symmetry with respect to the y-axis. So if you're able to take a graph and fold it over the y-axis and the graph overlap each other, then you know you're dealing with even function. So here's an example that you've seen before in the past. Y equals x squared is an even function. And the special property with even functions is that if I replace every x with negative x, it ends up going away. Reason why is because each of even function is going to cause a negative to go away. Anytime I'm squaring a negative value, I'm always going to get back to positive. So, and we have two special functions, two trig functions that fall under this even function category. And those are cosine and secant. So the special property with cosine and secant, this is the cosine graph. You can visually see how the cosine graph, if you fold the graph over the y-axis, they overlap each other. And secant is the same way, because secant is based off of the cosine. So here's the special property. If you ever see cosine of negative theta or secant of negative theta, because they're even functions, you can make the negative go away, because the negative will just get absorbed into the cosine function with no resulting impact. So any negative that is inside the cosine function will get swallowed up, and it will not. There's no more negative. Okay. So basically, cosine and secant, you can just make the negative go away. So those are the two that are even functions. The other four trig functions, those are odd functions. So odd functions are ones where there's a symmetry about the origin. Visually speaking, what that means is that if you can take a graph and if you can flip it upside down, and if the graph doesn't change at all, you're looking at an odd function. So the special property with an odd function is if there's a negative, if you introduce a negative inside an odd function, just pretend like you're taking that negative and you're just moving it out in front of the entire problem. So sine, cosecant, tangent, cotangent, they're all odd functions. So whenever you see sine of negative theta or cosecant of negative theta or tangent negative theta or cotangent negative theta, all you need to do is to take the negative and move it in front. So cosine and secant, they disappear, but the other four trig functions, if there's a negative stuck inside the trig function, inside of theta, just literally just move it out in front, because that's the resulting property for odd functions. Take the negative and just move it to the front. All right, let's try number one. Use trig identities above to simplify each expression. Cotangent of x, maybe we can do a little bit of converting, right? Cotangent of x can be rewritten as 1 over tangent x. What can we do with tangent of negative x, though? Take that negative and do what with it? Yeah, move it to the outside. That's what this property tells us. We can take a negative that's stuck inside that tangent, move it to the outside. So now we're left with 1 over tangent x times negative tangent x. Tangents cancels out. There's a negative left over, so negative 1. Okay, number 2. We can't do anything with cosine theta, so that will stay put. But is there anything we can do with secant of pi over 2 minus theta? Yep, we can shift it, and what does it turn into? Cosecant, yeah. Look at the very top. There's that property that we can use. Secant of pi over 2 minus theta equals cosecant theta. So we have cosine times cosecant theta. I can play with that secant, sorry, we play with that cosecant, right? Rewrite that cosecant as over sine. Cosine over sine is just cotangent. Give you guys a moment. Okay. So I'm going to do the classwork with you. The next page, the odds 5 through 23. We'll just get through as much as we can, and however much we get through, that will complete your classwork. And I just want to come around and just check you guys off. Okay. So is everybody still working on this page?
Can you scroll back up to the notes?
Mm-hmm. Okay, so for those of you who are ready, go ahead and go to the next page and copy down number 5. Now you may need a separate sheet of paper just because of the space that's not quite provided on that page. But I'll also work on a separate sheet of paper. Okay, is everybody okay?
So page 7, do you want
Yeah.
to do even and odd?
Oh no, we're doing the odds together. Yeah, we're doing the odds together. Okay. So page 7, let's start with number 5. Sine of theta equals 0.45. Find cosine of pi over 2 minus theta. Let's see. We know cosine of pi over 2 minus theta is same thing as sine. Yeah. And if this is equal to sine of theta, then sine of theta, that means this must be equal to what? 0.45, right? So no changes there. Okay, number 7. Sine of theta minus pi over 2. Something's a little bit off about this. Do you notice anything off about this? Do we see an identity that looks like this? Close, except what? Yeah. These are in opposite spaces. So what do you think is the relationship between this and this? Okay, it's going to be negative versions of each other. Okay, just a negative version of each other. So based off of this, I can conclude that, well, I know that this is equal to, I know that sine of, okay, so basically sine of theta minus pi over 2 is just negative, right? Just negative cosine. Okay, so I'm just going to hold on to that information for now. The rest of number 7 says find cosine of negative theta. Okay, what do you know about cosine of negative theta? Yep, it's an even function. The negative just gets swallowed up. So I basically just want to find cosine of theta. So I know that this is basically cosine of theta, except it's the opposite sign. Okay, some of these are repeats of what you've seen. Number 9, use basic identities to simplify the expression. Tangent of x times cosine of x, number 9. Convert that tangent to be in terms of sine and cosine. Okay, number 11. Okay, secant of y, maybe I can convert that to be in terms of cosine. Times. Do I have a suitable replacement for sine of pi over 2 minus y? Yeah. Yeah, theta and y are interchangeable, just the variable here. So that reduces to be just 1. All right, numerator and denominator just cancel each other out. Okay, 13. Let's find an identity for 1 plus tangent squared of x. Okay, just to let you know, there are multiple ways they can do to clean this up. You can either convert everything to be in terms of sine and cosine first, and then rearrange it, or I can just flip this up to be the reciprocal, which is sine squared, and then work from it. So I don't know if there's one clean way that's better than everything else, but as long as we're following rules, we should all be able to end at the same place. So one way I can do this, I can just go ahead and get all the conversions out of the way. And then just think, okay, if I just flip that denominator up, I can finish off the problem. This can be combined into one fraction, sine squared over cosine squared, which is tangent squared. Okay. We don't have an identity just yet because that cubed is a little bit high. But what do you think we can do if we have 2 terms here, cosine and cosine cubed? Yeah. GCF, right? There's a common factor that we can pull. They both have cosines in them. Divide both sides by cosine. Cosine divided by cosine. The leftover is 1. Divide cosine cubed by cosine. We're left with 2 cosines. And then 1 minus cosine squared x can be rewritten as trig identity. 1 minus cosine squared is sine squared. Yeah. So it doesn't clean up as nicely as the others, but this is as far as we can go. Okay, everybody go with 15. All right, here's 17. All right, is there something that we can do with cosecant of negative x? Is there a way to rewrite this?
What is negative 1?
Yeah, so that negative, you know that cosecant is not an even function, it's an odd function. We can just literally move that negative in front. And then we can convert that cosecant to be sine. The signs cancel out, but there's a negative 1 left over. Okay, let's see if any of these properties can be applied here. What can we do with cotangent of negative x? Yeah, hold that negative in front, right? How can I convert cotangent of pi over 2 minus x? Tangent. Cotangent is the reciprocal of cotangent is the reciprocal of tangent. So I can really think of it as negative 1 over tangent x times tangent x. Tangent goes away, but a negative 1 is left. Okay, 21. Sine squared of negative x plus cosine squared of negative x. I'm going to pull the exponent out just so that I can easier to kind of see what will be the results of these odd and even rules. So let's just ignore the square for a moment and let's just observe what happens within each of the sines and cosines. How can I rewrite that sine of negative x? And this? Well, cosine is an even function, right? Cosine is secant. The negative just goes away. It just disappears. So this will stay cosine squared x. What's going to happen here? Is that negative going to make any impact? It's still going to be positive, right? So this is essentially going to go back to all right. We did take care of that odd property, but it did revert back because that negative was taken care of by this outer exponent. So this is just equal to 1. Okay, last one here, 23. Okay, anything that I can do with that tangent of pi over 2 minus x? Cotangent, okay. Okay, any other cleanup things that we can do? Okay, rid of one of the cosecants. So now I'm left with cotangent over cosecant. Okay, what if I get everything in terms of sine and cosine? I should be able to get some more clarity here. So cotangent is cosine over sine. Cosecant is 1 over sine. If I'm dividing by a complex fraction, I can multiply the top by the reciprocal of the bottom. Which just gives us cosine.